Okay, so now we've seen where supply and demand curves come from and how they arise out of the profit maximizing decisions of firms or the utility maximizing decision making of individuals. Okay? They can take a lot of different shapes. It depends on the structure of the utility function for consumers and the mix of consumers that are out there, because we have to add them all up. It depends on the shape of the production function for firms and the mix of different types of firms that are out there, and how all their cost functions shake out. But at the end of the day, we end up with curves that look sort of like this, right? So we've got some kind of quantity that's supplied, and it goes up when price goes up. And we've got some kind of demand, and it kind of goes down when demand or when price goes down. I'm sorry, the quantity demanded goes down when the price goes up. Okay, they go in different directions. Okay, so if we want to characterize these things, one useful tool that matters a lot in economics is called the elasticity. And it's a way of describing sort of key features of demand, supply, or really any kind of curve. And let's first talk about we're going to focus on the price elasticity of demand at this stage, but you could also do the price elasticity of supply and lots of other things. So the price elasticity of demand intuitively means by what percent does demand change when price changes by, say, 1%. All right, when price changes by 1%. That's an approximate definition, but it gives you the intuition, okay? For example, if price increases by 1% and the elasticity is -1, then that means a 1% increase in price leads to a 1% decrease in the quantity demanded. You could also have like the elasticity equal to -1,000, which would mean a 1% increase in price leads to 1,000% decrease in demand, or really sharp, okay? Or conversely, a 1% decrease in price leads to 1,000% increase in demand, okay? So you can lastly say have an elasticity of, say, 0, which means that as you change the price, the effect on demand is zilch. They always demand the same amount. All of these are theoretically possible as long as they have as long as they're not positive numbers for demand anyway, because demand slopes down, and that's just something we sort of assume. We talked a little earlier about how there could be these things called Giffen goods where the price and the quantity go up, but they're so rare there's some debate about whether there's even any examples in the real world. Elasticity of supply is, on the other hand, the opposite way around. As the price goes up, usually the quantity also would go up, and so they would have a positive relationship. Anyway, this is the sort of intuitive understanding of what this thing is telling us. And essentially, it's kind of like a measure of slope. As you change one of the axes, what happens to the other? But it's a slope that's sort of defined in terms of percentages. And that's really useful because goods are so different that if we used like actual units, it wouldn't be that informative, right? Like the price of if you raise the price of cigarettes by $1, that's sort of a large change. Or you could think of something even smaller, like the price of a Coke. If it increased by $1, that's a large change. But if you raise the price of a Boeing 747 airplane by $1, that's like almost so small that it can't be seen, okay? More interesting to us is what happens to demand when we change the price of those goods by, say, 1% of their normal price, okay? That would be sort of more informative, and that's what elasticity is for. So this is the intuitive definition, but the technical definition that we use in this course, we define it with this little Greek symbol, and it's equal to the partial derivative of the quantity with respect to the price times price over the quantity. Okay? Why does this have anything to do with that? Well, let's rearrange it and we'll see. Okay? We can rewrite this as dq divided by q times P over dP, which we can rewrite as dQ divided by Q divided by dP divided by P. Okay? Now, this is basically saying, like, imagine dQ is a small amount, a small change in Q, and dP is sort of telling us a small change in P. Because remember, that's the intuition of a derivative is that it's like an instantaneous slope. So it's like the slope, if you made a very small change in P, what would the effect be on Q? Okay. So it's rise over run still. Now, a small change divided by the whole thing is actually about equivalent to a percent change. And the best way to see it is with an example. If I raise the price of something by $1 and it normally costs $100, that's like a 1% change in the price. Okay. If I increase the quantity of something that's normally 100 units of it by 5 units, that's like a 5% increase in the quantity. Okay. So we're basically saying a percent change in Q, and we're dividing it by a percent change in P, more or less. And that's the intuitive explanation too. So the question is, this is what it is mathematically. We actually have all the ingredients we need to find it. And so we can do an example here. All right. So suppose we have a Cobb-Douglas production function, which we've now learned gives us demand that looks something like this. So let's say we spend 1/3 of our income on food. This is a fine Cobb-Douglas production function. What's the elasticity of demand for this function? Well, first we need to find this, and then we can substitute in the prices and the quantity. In this case, since we're talking about food, Q is F, since we're measuring the quantity of food, and P is P of F. Okay? So we want to know what's the derivative of F with respect to PF, and then we need to multiply that by PF over F to get the elasticity. All right? So the derivative of this guy is easiest to see if we rewrite it like so. Instead of taking it as a denominator, bring it out front with an exponent of -1. Then we can see that the derivative of that, we can just use our normal derivative rule. We get -1 times 1/3 times y pf to the -2, because we've got to subtract 1 from it. Okay? And so if we substitute that in, we get -1/3 y divided by pf squared. Okay? Because we had a -2, and I'm putting it back in the denominator. We have to multiply that by pf over f. And this is the elasticity, but it's not very illuminating, and that's because we can actually simplify it a lot more. So we can cross this pf out and cancel it with one of the squared ones. Okay? And now we're left with -1/3 y over pf divided by f. Seems like we're almost done, but actually we know that f is equal to 1/3 y over pf. And that's exactly what's over here. So we're dividing this by itself. And so the elasticity turns out to just be -1 here. Okay? Let me say that again. We have 1/3 y over pf, and we're dividing by f, but f is also 1/3 y over pf. So they cancel out, and all that's left is that negative sign. So another interesting feature of the Cobb-Douglas function is that Cobb-Douglas utility gives you an elasticity that's everywhere constant. Okay, it's always equal to -1, which means that it's appropriate for any situation where if price increases by 1%, people's demand falls by 1%. If price rises by 1%, demand falls by 1%. If price falls by 1%, demand rises by 1%. They're negatively correlated. In the next video, we'll do examples for some other kinds of production functions, some other kinds of things, but I think that, this is the introduction that you need.